Okay, a couple more problems with limits. This is number 53 in the book. They give us a function which is a piecewise function. Okay, two different formulas, one which is valid when x is less than or equal to 3, another which is valid when x is bigger than 3. And of course, the limit they ask for, what does this function approach when x approaches 3? Okay. Now if you remember graphing these in algebra, each piece in this case is a straight line. Okay. And of course, the pieces of this function consist of one straight line to the left of 3 and another straight line to the right of 3. Okay, so the question is, when x gets close to 3, what y value do we approach? Okay. Well, generally speaking, it could be two different y values. Okay, because we have a formula that's valid to the left of 3 and another formula that's valid to the right of 3. Okay. So I'm going to actually look at those two cases. What happens when x approaches 3 from the left? Okay. So to answer this question, we're going to look at the left and right limits separately. Okay. Now the reason I look at the left and right separately is that I can use the replacement theorem. Okay. Now on the left side of 3, those are values of x which are less than 3. This is my function. Okay. 1/3 x minus 2. Okay. And there's no secret here. You can just put 3 in for x and get the y value out, okay? Because this one formula is valid to the left of 3, okay? So I can use direct substitution here. It's 1/3 times 3 minus 2. Okay, that's 1 minus 2, which is -1. Okay, so nothing strange here at all. I had a function. I replaced the function with a particular formula that's valid when x is less than 3. Okay, that's why I wanted to split this into two limits. The left side, I can replace f of x with a particular formula, and direct substitution is okay. Now, to the right of 3, we also need to see what happens. If these two limits don't agree, we'll have to say this limit's undefined. Okay. So to the right of 3, exact same idea, but now we're going to be using the other formula. Because when x is bigger than 3, this is how we compute the function. -2x plus 5. Okay. Well, -2 times 3 is -6, plus 5 is -1. So it turns out that both of these pieces of the function approach the same value when x approaches 3 from the left and from the right. Okay. So this limit is -1. Now, if they had asked us to limit as x approaches any value other than 3, there wouldn't have been any confusion at all. It's just 3 is sort of the problem because that's where our function is separating into two different formulas. If we had asked the limit when x was approaching 5, that's bigger than 3, so even to the left and the right of 5, this is the formula we would use. Okay. But because that's right where the transition occurred, it's a little tricky here. Okay, I'm going to do one other one, okay, and this is a similar one. Another one that eventually we're going to use direct substitution. And let's see, this is number 56 in the book, and they ask us to find the limit as delta x approaches 0 of 4 times x plus delta x minus 5 minus the quantity 4x minus 5. Okay, all over delta x. Okay, well, there's an x and a delta x in here, two variables really. But the first thing you'd realize is that you can't use direct substitution, because if we just replaced the symbol delta x with 0, we would be dividing by 0. Okay, and by the way, this limit looks very strange, but of course it's one of the limits we're going to see in the upcoming sections. Okay, it's similar in any case. Okay, so what do we need to do? Well, simplify with algebra. The idea is we want to use that replacement theorem. So hopefully maybe we can cancel this delta x with something. And in fact, I think that's what's going to happen. I want to try simplifying the numerator first. I distribute the 4 into the parentheses. I get 4x plus 4 delta x minus 5, okay, minus 4x plus 5, all over delta x. Okay. So a couple of things cancel. The -5 and the +5 cancel. The 4x and the -4x cancel. And all I have left is the limit is delta x approaches 0 of 4 delta x over delta x. Okay. So far, all we've done is use some algebra. Okay, but now we can actually use the replacement theorem. You see, we can cancel these delta x's, because as long as delta x isn't exactly 0, I can always cancel a factor in the numerator and denominator. And that's what the replacement theorem tells us. We're going to get the same limit as the limit as delta x approaches 0 of the number 4. Okay. Because the only time where we can't cancel this is when delta x is actually equal to 0. Okay. So what happens to the number 4 when delta x approaches 0? Well, there's no delta x here, so we just get 4. Okay. And that's the limit. Okay. So basically, all we're doing is we're canceling things that are a problem because they don't affect the limit. If they're a problem only when the variable is equal to that limit point, it doesn't matter. That's what the replacement theorem says. So this limit, after all this work, is just 4.